Hi, I'm Zhao. I'm a PhD candidate at University of California, Riverside. The paper I will be presenting today is titled Significantly Improving Lossy Compression for HPC Datasets with Second-Order Prediction and Parameter Optimization. This is my outline. First, I will talk about the motivation of lossy compressors. The first motivation is about storage capacity and I/O. Extremely large amount of data are produced by today's extreme-scale scientific simulations. For example, CESM climate simulation will generate 2.5 petabytes raw data. According to the expert, a data reduction factor of no less than 10 is needed in order to store this raw data. HAC, which is a cosmology simulation, will generate 20 petabytes of data per simulation. As comparison, Mira, which is a supercomputer at Argonne National Lab, only has 26 petabytes of storage and 240 gigabytes per second peak I/O speed, which means the HAC simulation will occupy more than 80% of storage of Mira, and it takes longer than 24 hours to store the data. Another motivation is about data transmission and streaming, because many scientific simulations need to transfer data from one place to another, and they usually has high generation speed with large amount of data. One example is the advanced photon source at Argonne National Lab. It needs to transfer 15 petabytes of data from APS to Mira for post-processing, but the network bandwidth is only 100 gigabytes per second, which means the transfer time is longer than 14 hours. Another example is LCLS at Stanford University. It has 250 gigabytes per second acquisition speed, but the writing bandwidth is only 25 gigabytes per second, which means 90% of data will be discarded. The figure on the right-hand side is the data reduction pipeline for the LCLS. The figure in this page demonstrates some statistics of state-of-art supercomputers. We can see from Titan to Summit, there is a 6-time system peak performance increase. However, the storage capacity increase is only 4 times. And unfortunately, the I/O speed stays the same. So in conclusion, storage capacity and I/O speed increase cannot catch up with computing speed increase. Under this condition, many scientific simulations use compression technologies to store the data. And for compression, there are 2 different types of compression methods. The first one is lossless compression, which means the data is compressed and decompressed in such a way that the decompressed data is identical to the initial data. gzip is an example of lossless compressor. The second type of compression methods is lossy compression. For lossy compression, the data is altered during the compression process. So some piece of information is removed and the original data cannot be retrieved. If a user can control the accuracy of the compression data, then lossy compression is a trade-off between data size and data accuracy. For scientific data sets, lossless compression cannot lead to a high reduction ratio because the ending metadata of scientific data usually looks very random. So directly applying encoding to scientific data does not work efficiently, and advanced lossless compressors, which exploit further reduction, do not have a very good compression ratio. So this figure shows that for many lossless compressors, they only have less than 2.5 for compression ratio on scientific dataset. Under this condition, lossy compression becomes a very promising solution. There are two major requirements for lossy compressors. The first one is arrow bounded, which means the accuracy of the decompressed data need to be controlled. And there are two types of arrow bounds, absolute arrow bound and relative arrow bound. In this paper, we focus on absolute arrow bound. The second requirement for lossy compressors is to have high compression and decompression performance, because lossy compressors need to be used for in situ analysis. The compression quality of lossy compressors is usually measured by rate distortion graph. The x-axis of rate distortion graph is bit rate and the y-axis is distortion, or PSNR. The more upper left the curve, the better the result. The figure on the left-hand side shows that for QMC pack dataset, ZFP has a better compression quality than SA. The middle figure shows that for NICS Bayesian density field, SA has a better compression ratio than ZFP. The figure on the right-hand side shows that for the temperature field of NICS dataset, it's hard to tell which compressor is better than other one. And existing lossy compressors can be categorized into two different types. The first type is prediction-based compressors, including Isabella, HPC, and SZ. The second type is transform-based compressors, including Vapor and ZFP. SZ and ZFP are two state-of-the-art compressors, and we will compare our solution with them in the experiment section. Since our solution is based on the SA compressor, I will give more details about SA in this page. SA is a prediction-based compressor. It uses Lorenzo and regression predictors for data decorrelation, and it uses linear quantization to respect the arrow bound. The figure on the left-hand side is a demonstration of Lorenzo predictor and regression predictor. For Lorenzo predictor, the prediction value of current data point is calculated using the values of its neighbors. For regression predictor, a hyperplane is selected using the original least squares methods, and the prediction value is calculated using this hyperplane. The figure on the right-hand side is a demonstration of linear quantization. So linear quantization tries to store the differences between the prediction value and the original value, and it stores this with respect to the arrow bound. This is the overview of our solution. There are two major contributions in our paper. The first one is that we improve the data prediction accuracy by using second-order predictors, including second-order Lorenzo predictor and the second-order regression predictor. The second contribution is that we determine the best parameter settings for the overall compression. So for this contribution, we introduce a lightweight sampling engine, offline parameter optimization process, and an online parameter optimization process. The figure demonstrates the architecture of our solution. So we replace the prediction module with the compression quality optimizer. So for this optimizer, it includes a sampling engine, parameter optimization, and blockwise prediction engine. Second-order Lorenzo predictor was proposed by some other researchers, but they didn't use it for the compressor because they didn't get a good compression ratio. However, we found that second-order Lorenzo predictor is better than first-order Lorenzo predictor when the error bound is relatively low. So the figure on the left-hand side demonstrates the second-order Lorenzo predictor. Instead of using 3 neighbors, second-order Lorenzo uses 8 neighbors to calculate the current prediction data. And the figure on the right-hand side has the quantization bin distribution between first-order Lorenzo and second-order Lorenzo predictors. For this distribution graph, the sharper the distribution, the better the compression ratio. So for all the 4 figures, second-order Lorenzo has a better compression ratio than the first-order Lorenzo. Second-order regression predictor finds the quadratic hyperplane that most closely fits the data by ordinary least squares method. As comparison, first-order regression uses the linear hyperplane. So quadratic hyperplane will have better prediction accuracy than the linear hyperplane. And the coefficients of second-order regression are compressed using SC compressor. The figures on the right-hand side are the distribution of quantization bins, and we can see that for all the 4 figures, second-order regression is better than first-order regression. Our second contribution is about parameter optimization. Parameters are used to control block size, prediction dimension, quantization, and so on. SA has 5 parameters. Since we introduced second-order prediction, we bring 7 more parameters. Parameter settings affect the compression quality dramatically. The figures on the left-hand side show the relationship between block size and compression ratio. For example, for figure A, the blue line compression ratio will be 200 when block size equals 5. But for the red line, the compression ratio will be its highest when block size equals 3. So it's very hard to choose the default value for the block size in order to have highest compression ratio for all datasets. The figure on the right-hand side is the number of quantization bins with compression ratio. So for the right line, the compression ratio will be its highest value when number of quantization bins equals to 8192. However, for the blue line, the compression ratio will be its highest when the number of quantization bins equals to 1024. So also this shows that it's also very hard to choose the default value for the number of quantization bins in order to have the highest compression ratio for all cases. To solve this problem, we propose 2 processes. The first one is offline optimization. For this process, we test more than 30K combinations of parameter settings. The test values are selected based on our experiments when measured data size. And after this optimization, we generate outstanding candidates, which have high probability to achieve top compression ratio. And for online optimization, we will test outstanding candidates to find the best settings as parameters for the current dataset. To improve the speed of online parameter optimization, we need to use sampling engine to generate a sampling dataset to use instead of the original dataset. So we also proposed a new compression principle-based sampling engine. For this engine, we ensure that sampled block size is consistent with the block size in compression steps, and it leverages data points from other adjacent blocks to estimate the prediction accuracy in each block. The figures on this page demonstrate that our sampling engine has more accuracy than the black box estimator, which was proposed by other researchers. For evaluation, we use Bebop at the Argonne National Lab. Bebop, we use up to 128 nodes, each with 2 Intel processors and 128 gigabytes of memory. Each processor has 18 cores. The I/O system is GPFS with 2 I/O nodes in total. We use 5 datasets, including Hurricane, Miranda, Clumsy Park, Scale, and Nix. They are from different domains, including weather, hydrodynamics, autumn, and cosmology. They represent a wide variety of scientific simulations. First, we present the percentage of predictors used by block. We can see that when the error bound is relatively small, the second order Lorenzo predictor will be more popular than the first order Lorenzo predictor. And when the error bound is relatively large, the second order regression predictor will be more popular than the first order regression predictor. So this confirms that second order Lorenzo and the second order regression predictors are better than the first order predictors under some cases. And in this page, we show the breakdown with distortion of second order prediction and the parameter optimization. The black line is SA, and the blue line is second order prediction. And the red line is second order prediction with first order prediction and parameter optimization. So we can see when bit rate is relatively large, the second order prediction is better than first order prediction. And even for those bit rate range, when the first order prediction is better, we still use parameter optimization to improve the compression ratio or compared to the baseline of SD. This is the overall distortion of our solution with state-of-art compressors, including SD and ZFP, and a hybrid model. Those figures demonstrate that our solution exhibits the best compression quality among all existing compressors. And we have a compression ratio improvement that up to 53% over SD. And to show that our solution can be applied to new datasets, we did an evaluation for multiple QMC pack datasets. So QMC pack dataset 2 and 3 are not used for offline parameter optimization, and they are largely different with QMC dataset 1, which is used for offline parameter optimization. And the result of our online parameter optimization for QMC tag dataset 2 and dataset 3 show that our solution still can improve the compression ratio by up to 54% for the new datasets. And to show the performance of our solution, we did a parallel evaluation. First, we use visualization on the left-hand side to demonstrate that we have the high precision of the reconstructed or decompressed data. And the figure on the right-hand side shows that our solution has the least overall elapsed times, which are 20 to 40% less than the second best compressor. For the future work, we plan to explore better predictors, including neural network-based predictors and self-adaptive predictors. And we also will explore better sampling engine that has higher estimate accuracy with less runtime. And at last, this work was supported by the ECP project. And we acknowledge the computing resources provided on Bebop, which is operated at Argonne National Lab. That's all. Thank you.